Hi everyone. Earlier in our discussion of basic memory management, we learned that the Translation Lookaside Buffer or TLB, which is part of the MMU, it plays a critical role in speeding up memory accesses. So here we will discuss how TLB coverage can be improved, meaning how we can translate a larger range of virtual addresses to physical addresses without doing a page table walk. And as part of that, we will also discuss the idea of superpages or large pages that are primarily meant to increase the TLB coverage. This lecture is primarily referring to the paper by Navarro, Iyer, Druschel, and Cox from OSDI 2002. You can find that paper from the link that's posted on the slide. So what is the problem we are addressing? We know that TLB is used to cache virtual to physical page number mappings. The more the number of mappings stored in the TLB, the fewer TLB misses we have, and the MMU has to do fewer page table walks. So over the years, uh, the size of the TLB has increased as processors have become more advanced. But at the same time, applications have also been using more and more memory. So in other words, the working set of applications, that is the amount of data applications need to be in memory in order to work effectively, has grown in size. The problem is that uh, the this increase in the size of the TLB has not kept pace with the increase in the working set size of applications. So in response to this, uh, there is only so much that architecture designers can do to increase the size of the TLB. So the other option is to increase the size of the pages itself. By doing so, each TLB entry can now translate a larger sized page and hence a larger portion of the virtual memory. Unfortunately, at the time this paper was written, most operating systems were slow to harness large pages or super pages. And in particular, user level applications did not have a transparent mechanism to benefit from these super pages. So this paper was the first one to address this problem, which is how user level applications can transparently benefit from using super pages and hence lower TLB misses during their execution. So a brief review of what TLB is and what it does. So TLB is a cache, but it's not a data cache or an instruction cache. It is a cache that's part of the MMU, and it is used by the MMU to store frequently used virtual to physical address translations, or specifically virtual to physical page number translations. So TLB coverage is the amount of memory that can be translated using the TLB entries without having to do a page table walk in memory. So in other words, if the more the amount of memory that can be translated using the TLB, the fewer the TLB misses we have. So at the time this paper was written back in 2002, the typical TLB coverage was about 1 megabyte, right? And the goal was how we can increase the TLB coverage. So one solution is to use pages that are bigger than normal pages. So normal pages in most architectures and operating systems is about 4 kilobytes. And if we say double the size of the page to 8 kilobytes, then suddenly the coverage of our TLB increases by a factor of 2. So uh, uh, so what these authors of this paper want to do is they don't just want to use a single super page size. They want to use pages of different sizes, large pages and small pages. and use them as per the needs of the application. So by doing so, you can increase the TLB coverage without having to increase the number of entries in the TLB, or without having to increase the TLB size. So to be more precise, what are these super pages? Again, the super pages are referred to by different names over time. They are also called large pages or huge pages in different contexts. So super pages, as the name suggests, it's pages bigger than the normal page size or the base page size. So you cannot just arbitrarily pick a page size. These are architecture dependent. They are specified by architecture designers. Normally super pages are powered to the 2 times the base page size. So for example, you can have a super page of size 4 kilobytes, or 2 times 4 kilobytes, which is 8 kilobytes, or 4 times 4 kilobytes, which is 16 kilobytes, and so on. But you cannot have a super page of, say, 12 kilobytes, which is 3 times 4 kilobytes, because 3 is not a power of 2. So if you have a super page, then the entire super page will use only one TLB entry, meaning that a single TLB entry can be used to translate all the memory references within that super page. But there are also certain constraints on super pages. So for one, the entire super page should be contiguous in physical memory and virtual memory. What that means is, if a super page consists of, say, 4 base pages, then all the 4 base pages must be next to each other in the virtual address space, and the corresponding in the physical pages, the base pages should also be next to each other in physical memory. Another requirement is they must be aligned physically and virtually. What this means is that you can only start a super page at a boundary which is the multiple of the super page size. For example, a super page of size 8 can start at address 0, or address 8 kilobytes, or address 16 kilobytes, or 24 kilobytes, and so on. But it cannot start at, say, an address of 4 kilobytes or 12 kilobytes. And there's one more restriction on the use of super pages if the earlier restrictions are not enough. So since a super page consists of multiple base pages, all the base pages will have uniform protection attributes, meaning the ability to read or write to the super page, or whether the data there is executable code, and so forth. So you cannot have base pages having different protection attributes. So this prevents us from doing things like mixing code and data within the same super page. And finally, there's only one reference bit and dirty bit. As we saw before, that these reference and dirty bits are used by the operating system to keep track of frequently used pages, and also which pages need to be swapped out. So this picture shows how a single TLB entry can translate a super page from virtual to physical addresses. So here the green page here is a base page of, say, 4 kilobytes, and in the TLB there will be one entry that translates the base page into its corresponding physical address. And there is some indication through either a field or by having separate TLBs that this is a base page of size 1. On the other hand, there is a super page of size 4 in the virtual memory, and this also uses a single TLB entry, just like a base page of size 1. But then when you translate it, it would give us the base address of a super page in physical memory, which again is of size 4 base pages. So as you can see, although we are using only a single TLB entry, but now we can translate a larger portion of the virtual memory to its physical addresses. So again, this is the super page sizes that are available are architecture dependent. For example, at the time of writing this paper, the alpha architecture supported super pages of size 8 kilobytes, 64, 512, 4 megabytes, and so on. Similarly, Itanium architecture supported a range of superpages all the way up to 256 megabytes. So now we're going to get into specific problem statements. Now, architectures provide these superpages, so why can't we just use them? It turns out that we have to do a little more work. Specifically, the operating system has to do a little more work in order for normal user level applications to use these superpages. So the very first problem is the superpage allocation problem. This problem is at what point does the operating system decide to allocate superpages? How does it allocate these superpages, and what size does it choose? Remember, we now have a mix of superpage sizes, so we have a choice. It's not a single superpage size for all requirements. So in this picture, you can see that in the virtual memory there's a base page B, and there's a corresponding physical page B. Now, as the application accesses neighboring pages A, C, and E, if we were not using super pages, then the operating system would go ahead and allocate base pages all over the physical memory. And you can note that in the physical memory, these physical pages are not next to each other. So if we want to construct a super page out of these 4 base pages, we can't do it right away because of all the restrictions that we discussed earlier, particularly that the base pages have to be contiguous and aligned in physical memory. In order to construct a super page, we could choose to bring them all, move all the base pages into a region of physical memory that's contiguous, and at that point we can construct a super page, and we can then avoid the extra TLB misses. So once we create a super page somehow, the question is, how do we are we just stuck with a particular super page size, or could we promote it to a larger super page size? So in this picture here, we have 4 base pages that are next to each other, and then a 5th base page that's contiguous, but it's on a separate alignment boundary. Now, we could wait for the application to touch those additional 3 pages and then create a super page. If we wait, then we lose the opportunity to reduce TLB misses ahead of time. On the other hand, we could be opportunistic, and we could create a super page of size 4 and then create a super page of size 8 later. However, promoting a super page to a higher size may incur additional overhead in terms of memory management and work done by the operating system. Or we could be eager and say, all right, we'll just create a super page of size 8 by forcibly populating these physical pages from elsewhere. And if we do that, then the application is not using those additional pages. So as a result, nobody else can use those additional pages, and there is increased internal fragmentation. So with these, and then there is a third problem, which is that we don't want to just keep creating super pages. At some point, we may have to demote these super pages back to their base page sizes. So the question is, what point do we demote these super pages? Because if we don't do that, in the end, we would just end up with larger and larger super pages in the entire physical memory. So normally you want to demote these pages when, let's say, the attributes of the base pages may change. For example, when you're mixing code and data into a common super page, so their base attributes become non-uniform. Or let's say you need to page out some memory in response to memory pressure. Then you don't want to page out a full super page, so you could demote it, and then you want to page out parts of the super page. But this is not easy, as we will discuss very soon. Finally, there is an issue of fragmentations, particularly both internal fragmentation and external fragmentation. As we saw earlier, that if you have a large superpage size, if you assign a large superpage to an application and it doesn't use the whole superpage, we are wasting memory. That is internal fragmentation. But then with superpages of mixed sizes, we also have a return of the external fragmentation problem. Particularly, if you have a superpage of size 4 and 8 and 16 and so forth all over the physical memory, then then there may be certain chunks of free memories, memory regions that are spread all over the physical memory. And if you want to create a superpage of, say, a particular size, we can't find enough contiguous base pages at one location. So as we keep using superpages of different sizes, this fragmentation problem at superpage granularity becomes worse. So we need some way to restore contiguity of free pages. The more base pages that are contiguous to each other, the more flexibility we have in allocating a superpage of a particular size that we want. So, of course, these authors were not the very first people to address this problem. There were numerous other uh, uh, people who had looked at different aspects of this problem. Some people had proposed reserving certain pages for superpage sizes. Some people had proposed mechanisms to relocate pages to provide superpage promotion. Certain architectures like IRIX and HPUX, they allowed user applications to specify the requirement for super pages, but again, this was not transparent to applications. In contrast, here we want to allow any generic application to benefit from super pages. People had investigated hardware support for super pages where you don't need to have contiguous physical pages. And then finally, no one surprisingly had addressed demotion of super pages back to base pages up till this point. So next we are going to look at the solutions that these authors propose to these problems. And their key observation is that if you want to provide superpage support transparently, then you have to somehow guess what is the superpage size that an application needs. And in this particular case, the rule of thumb that they use is that they're going to take hints from what the application is doing. For example, if the application allocates an array and it's about to initialize the array, then you want to create a superpage that is approximately the size of the array. Or if an application is opening a file, then if you know the size of the file, you can create a superpage of that particular size. But at the same time, they don't want to pay penalty in terms of performance overhead if there is a wrong decision. They want a mechanism to walk back a wrong decision. That is, if they allocate a superpage size that doesn't seem to be needed. So we will start with the allocation problem. For superpage allocation, they propose a mechanism called preemptible reservation. What that means is that let's say in this, going back to the earlier example, an application uses the base page B, and we know that the data object around the base page B is of size 4 base pages. So what we're going to do is we won't create a super page of that particular size right away. We're going to reserve the neighboring 3 pages around B in the physical memory with the expectation that the application will use these very soon. Which means that we are not going to allocate these physical pages to any other page in the virtual address space. And if our guess is correct, then application will soon use these neighboring pages, and we would have contiguous and aligned base pages in both physical and virtual memory. And then we could happily promote this into a super page of size 4. All right. But then you notice that the name says preemptible reservations, not just reservations. Preemptible means that we could cancel the reservation if needed. So what that means is that, so we guess what is the size of the superpage that's needed, and we would try to be as close to the size of the memory object as possible. And then if the application doesn't use it within, say, a certain amount of time, and some other application needs a superpage, or some other part of the virtual memory of the same application needs a superpage, then we can cancel the old reservation and use those base pages for another reservation. For example, here, in their paper, they propose a scheme where you maintain basically lists of existing reservations. So, and each of these lists is numbered depending upon the size of the superpage that we will get if we preempt the corresponding reservation. So if we preempt a reservation which is labeled in the list 4, then we will get a superpage of size 4, which consists of the 4 black pages, base pages in that list. Likewise, if we preempt a reservation in list 2, then the maximum superpage size reservation size we can get there is size 2, because those are the ones that are contiguous and aligned. All right. So when let's say that we want to allocate a new superpage, we can't find contiguous base pages elsewhere, then we would go to this reservation list and we will pick the reservation that's at the front of this queue of the corresponding list, and then we would cancel that particular reservation. So for example, if we wanted a superpage of size 4, we'll go to list 4, we would cancel that reservation, and we get 4 contiguous free base pages for a corresponding superpage reservation of size 4. The second part was promotion, the second problem. So let's say we have a superpage of a certain size. How do we increase its size to a larger superpage? So here we have a reservation of size 8 when the application starts using the base pages. So we don't wait till the application uses all the 8 base pages. We first create a superpage of size 2 as soon as the application touches those pages. And then later when the application touches 2 more pages, then we promote that to a superpage of size 4 and so forth till we reach a superpage of size 8. And this doesn't have, these accesses don't have to be sequential. I mean, the application could touch 2 base pages at the beginning of the reservation, 2 base pages somewhere in the middle of the reservation, and we appropriately promote those base pages to the corresponding superpage sizes. So this promotion policy is opportunistic. We take advantage of opportunities to increase TLB coverage wherever possible. And then the demotion problem, when do you demote superpages? Since there is only one reference bit and one dirty bit per superpage, we have to come up with some mechanism to detect when there is memory pressure, which superpages to demote, and what do we do with that. So if there is memory pressure, meaning that the memory in the system is running, free memory in the system is running low, then periodically the operating system goes around and resets the reference bit of all the pages, and at that time we could demote superpages back to the to their base pages. And then we could re-promote the superpages incrementally as and when application starts accessing those pages again. And let's say that a page daemon selects one of the base pages, the page replacement mechanism selects one of the base pages as a victim page, then at that point we demote the whole superpage into the corresponding base page. There's another issue to consider, which is that we don't want to write an entire superpage into the disk if it is selected as a victim page. So, but then we only want to write parts of the superpage that are actually dirty, means that have been updated by the application. So here, what we're going to do is, when upon memory pressure, we will mark all superpages as read-only. So what that does is, if an application tries to write to any part of the superpage, then that would trigger a write fault. And as a result of the write fault, the operating system can demote that superpage into corresponding base pages around the location of the write fault, and then we can re-execute the write operation on just that base page. This way, if we need to uh, swap out the page, only the base page needs to be swapped out. We don't have to swap out the entire superpage. So next, we discuss the issue of internal and external fragmentation. So the authors propose to modify the page swapping mechanism, specifically page daemon, so that it can periodically restore the contiguity of free base pages. So if you have uh, uh, clean inactive pages, you can move them to the free list. There's and then when you want to swap out pages, you choose victim pages that can contribute the most to contiguity. The plain least recently used algorithm would simply pick the page that hasn't been used for the longest time. But now we have one more consideration, that does this victim page contribute to increase in the number of contiguous base pages. Another aspect is clustering wired pages. What this means is certain pages are marked as pinned in memory, meaning that page daemon is prevented from swapping these out. If these wired pages are spread out all over the physical memory, then we cannot assign the base pages around that wired pages for super pages. So as a result, we need to uh, uh, at the initial OS initialization time, we need to set aside certain part of the physical memory as dedicated to wired pages or pinned pages, and then that way the rest of the physical memory remains available for use in super pages. So the authors didn't just propose this mechanism; they also went through extensive evaluation to, to demonstrate that their mechanisms are useful in practice. So to justify the complexity of implementing all these mechanisms in the OS. So they used the FreeBSD operating system for their prototype. Their hardware had an alpha processor and which supported 4 superpage sizes from 8 kilobyte to 4 megabytes. The hardware processor also had 2 TLB and 128 entry data TLB and 128 entry instruction TLB, and they ran unmodified benchmark applications to show that using their scheme they can perform better than if they didn't use their scheme. So here's a summary of all the performance improvements they saw. So if you just look at TLB miss reduction, then they generally observe that 95% of TLB misses are or more are avoided. But reduction in TLB miss doesn't automatically translate into a speed up for the application. So if they look at how much individual benchmarks were speeded up for spec CPU 2000, which is a standard industry benchmark, the integer benchmark within that benchmark suite, it improved by about 11% on the average from 0 to 38%. The floating point improved up to 83%, but in some cases it also lost performance by minus 1.5%. Which kind of is surprising, right? But then if you think about it, this reflects that sometimes their mechanism made wrong guesses. That is, it created superpages where superpages were not required, and they had to undo the effect of their wrong decisions. There were other benchmarks, fast Fourier transform, matrix transport. Again, these gave pretty impressive performance improvements. And out of 35 benchmarks they tried, 8 of them had 30+% improvement, which is pretty good. But then the question is, could we get the same performance improvement if we didn't use a mix of super pages size? What if we just use a single base page size for all super pages? So they did a performance comparison for that scenario as well. They took various super pages sizes here, 64, 512, and 4 megabytes. And they said, what if all the super pages of a particular size, and how much would their performance improve? So as you can see from this figure that if the last column is their mechanism where they use a mix of superpage sizes. So in all cases, they do at least as well as they get as much performance improvement as the best among the single superpage sizes. But in some cases, like MCF benchmark, they get much better performance improvement than any single superpage size. So what this shows is that it takes the guesswork out of the application developer's hand. You don't have to think what superpage size you just need to use. You just run their scheme, and most likely it would give you the best possible performance, whether it's or better performance than a single superpage size. In conclusion, this work demonstrates that superpages can be transparently supported for user level applications. The contribution of this paper is not just in proposing solutions, but also in identifying the problems and putting them in this framework, saying that OS has to address the allocation, promotion, demotion, and fragmentation control problem. And it turns out that the fragmentation control or contiguity restoration is a very critical part of their mechanism. Like if you don't have contiguity restoration, then over time the memory will get more and more externally fragmented at superpage granularities, and there will be fewer and fewer benefits. And they also showed that using multiple page sizes are important. A single superpage size may not work well for all applications, right? So superpages have since found their way into many other operating systems, particularly Linux as well. Linux has support for superpages in a couple of ways. Huge TLBFS for accessing certain memory mapped files, and also transparent huge pages for applications to request large sized pages. So feel free to browse more, and there's also this Wikipedia link which can give you more information for a range of operating systems and architectures.